scholars, welcome to another Smash JAMB series, and today we'll be smashing the topic capacitors in JAMB Physics. Now let's go straight to business. What is a capacitor? A capacitor is a device that stores electrical energy. All right, a capacitor is a device that stores electrical energy, or like some people will say, electric charge. Capacitor is a device that stores electrical energy or electric charge. Now, there are some other uses I would like you to know about a capacitor. I also want you to know some other uses of a capacitor. Now, a capacitor is used for voltage reduction, a capacitor is used for fluctuation in an electronic circuit. Now, another one I would like you to know is that it is used for smoothing signals, which is some people also, or some persons also refer to as circuit filtering. So a capacitor can be used for voltage reduction, can be used for fluctuation in an electronic circuit, and also it can be used for smoothing signals, which can also be referred to as circuit filtering. Now, let's move ahead. Now, I'd like to share with you the symbol for a capacitor, so that when you see a capacitor, you know you're dealing with a capacitor. This is the symbol of a capacitor. All right, this is the symbol of a capacitor. Now, the legs of these legs are the same height. All right, they are of the same height. So this is the symbol of a capacitor. Right, so when you see this, you know that you are dealing with a capacitor. Now, capacitors can be connected in series and in parallel. Capacitors can be connected in series and in parallel. Now let's move on to that. So let's look at series connection and parallel connection of capacitors. Now, for series connection of a capacitor is said to be connected in series, or capacitors are said to be connected in series when they are connected end to end. So this is C1, this is C2, this is C3, and then this is the voltage that is flowing across them. So capacitors are said to be connected in series when they are connected end to end. All right, end to end. Now, some of the concepts I want you to know in a series connection of capacitors, or in series connection of capacitors, is that these capacitors have the same charge flowing through them. They have the same charge flowing through them. So if this was the total charge in the capacitor, and let's say we have Q1 flowing through here, Q2 flowing through here, Q3 flowing through here. Now the total charge is going to be equal to Q1, is going to be equal to Q2, is going to be equal to Q3, because the same charge flows through each of these capacitors. Each charge on these capacitors is equivalent to the total charge in this circuit connected in this connection of capacitors in series. Each charge, the charge on this capacitor is the same, charge on this capacitor is the same with this, all of them are the same, and they are also equivalent to the total charge in these capacitors connected in series. Now, another thing I would like you to know is that the voltage on each capacitors are different. Let's say we had V1 flowing through here, we had V2 flowing through here, and then we have V3 flowing through here. The voltage on each of these capacitors are going to be different because they are connected in series. So Let's say this is the total voltage. The total voltage is going to be equal to V1 plus V2 plus V3. V1 plus V2 plus V3. So the total voltage is going to be equal to V1 plus V2 plus V3 because the voltage on each capacitors differ. The voltage flowing through here is not the same voltage flowing through here, is not the same voltage flowing through here, but the charge flowing through each of them are the same. Right? Now, for us to get the total capacitance in capacitors connected in series, or the equivalent capacitance for capacitors connected in series, we use the formula 1 over CT, or some people write this as CEQ, which means the equivalent, all right, capacitance. So 1 over CT is going to be equal to 1 over C1 plus 1 over C2 plus 1 over C3 plus 1 over Cn. As many capacitors as you have, all right, as much or as many capacitors you have connected in series. We are going to use this formula to find the total capacitance or the equivalent capacitance. The total capacitance or the equivalent capacitance. Now, another thing I would like you to know before we move further to parallel connection is that when two capacitors are connected in series, we use the formula C1 C2 over C1 plus C2. C1 C2 over C1 plus C2. We use C1 C2 over C1 plus C2. Take note, for two capacitors connected in series, only two capacitors. Note, this works for only two capacitors. You multiply them divided by adding them. Right? Now, let's move on to parallel connection of capacitors. As you saw earlier, the board was already full, so there was no way I was going to explain parallel connection. But now let's go straight to parallel connection. Now, capacitors are said to be connected in parallel when they are connected across each other. Across each other. So this is the voltage flowing across them. Let's say this C1, this C2, and then this C3. All right. Now, so they are connected across each other. Or you can also, if I bend the board, you're going to see like this too. So when they are connected across each other, they are said to be connected in parallel. Now, concept I want you to know when capacitors are connected in parallel are this, that the same voltage flows through them. So if this is V1, this is V2, this is V3, and let's say this is VT, that's the total voltage. The total voltage is going to be equal to V1, is going to be equal to V2, is going to be equal to V3. Because the same voltage flows through each capacitors. The voltage flowing here is the same voltage flowing here, is the same voltage flowing here. And it's also equal to the total voltage flowing through these capacitors. Now, another concept I want you to know is that the charges on each capacitors here are not the same. The charges stored by each capacitors here are not the same in parallel connection. So, say we had the total charge. The total charge will be gotten by Q1 plus Q2 plus Q3 because the charge stored on each capacitors are different. So the charge flowing through C1 is not the same charge flowing through C2, is not the same charge flowing through C3. They have different charges flowing through them. So take note of this. Now, for us to find the total capacitance for capacitors connected in parallel or the equivalent capacitance. Now, how do we do that? We say CT or CEQ, right, subscript EQ, that's either the total capacitance or the equivalent capacitance. Is going to be C1 plus C2 plus C3 plus as many as possible numbers of capacitors you have in that circuit connected in parallel. So to find the total capacitance or the equivalent capacitance, we use C1 plus C2 plus as many more capacitors as you have. All right, so that is what you need to take note of. Now this will lead us to the next phase of capacitors. We are going to look at the work done and the energy stored in the capacitor. So now let's look at work done. I'll just give the formulas. Now the work done in a capacitor is QV. All right, that is the charge multiplied by the voltage. The charge multiplied by the voltage. So work done in a capacitor is QV. Now energy stored in a capacitor is equal to half CV squared. Now I also want you to know that Q, charge itself, is gotten with CV. All right, Q is the charge here and it is gotten with CV. For us to get the charge of a capacitor, we use CV. That's the capacitance multiplied by the voltage. Work done is charge multiplied by voltage, and energy stored in a capacitor is half CV squared. Now before we move further, I want you to know that capacitors are measured in farad. Represented with F, capital letter F. So capacitors are measured in farad. Now charge is measured in coulombs. Right, let me write that here. Charge Q is measured in coulombs, abbreviated as C. Right, so charge is measured in coulombs and capacitors are measured in farad. These are key points you need to take note of. So coming back to this, the charge stored on a capacitor is CV. That's the capacitance multiplied by the voltage or the potential difference, and then work done is QV. That's the charge multiplied by the voltage. Now then energy stored in a capacitor is half CV squared. Now if Q is equal to CV, meaning that I can also manipulate this energy stored, meaning I can also write energy stored as another formula for energy stored in a capacitor can also be written as half QV. Take note of this. Half QV. Now how is that possible? Now let's come to this. You have that energy stored is half CV squared. I can split this to be E is equal to half CV multiplied by V, because V times V, that's giving me V squared, and CV alone from here is Q, so that gives me E is equal to half Q then multiplied by V. All right, so that's how we came about this formula. So energy stored in a capacitor is also half QV or half CV squared. Work done is QV, and charge stored in a capacitor is CV, the charge stored in a capacitor. Do not forget, capacitors are measured in farad. And also the unit for charge is coulombs. That's charge is measured in coulombs. All right. Now sometimes you see something like microfarad or you see something like millifarad. All these are some multiples, because micro has a value of 10 to the power of minus 6. Milli has a value of 10 to the power of minus 3. All these are some multiples and they are very, very important. They are usually attached with the values of capacitors. So make sure you understand them, right? Because they are very, very important. In the description of this video, I'll post the link, right? In the description of this video, I'll paste the link so that you can understand what submultiples are. Now, let's move to smashing JAMB past questions on capacitors. The purpose of a dielectric material in a parallel plate capacitor is to, we are given the following options. A, is it to increase its capacitance? B, to decrease its capacitance? C, is it to insulate the plates from each other? D, is it to increase the magnetic field between the plates? Now, One of the most popular type of capacitor is the parallel plate capacitor. Parallel plate capacitor. So the parallel plate capacitor has two plates which is separated by a dielectric material. So the dielectric material separates the plates. It separates the plates, and some other things it does is that it increases the capacitance of the capacitor. So it increases the capacitance of the capacitor by reducing the electric field between the plates of the capacitor. Now, so we're asked, the purpose of a dielectric material in a parallel plate capacitor is to increase its capacitance. Yes, the dielectric material increases its capacitance, like I said, by reducing the electric field between the plates. By reducing the electric field between the plates. Now, don't make the mistake of saying insulate the plates from each other. It does not insulate the plates from each other. It separates the plates from each other. The resultant capacitance in the figure below is now this is 2 microfarad, 3 microfarad. These two are connected in series, end to end. So they are connected in series. Take note. Now these two microfarad and the 4 microfarad, they are connected in parallel, and this is connected at the end of this. Now let's see how we can get the resultant of this capacitance of the capacity of these capacitors, all right, connected here. Now the first thing we'll have to do is that these two, all right, 2 and 4, that's 2 microfarad and 4 microfarad capacitors, they are connected in parallel. So resolve them, combine them. So how do we do that? When capacitors are connected in parallel, what do? We add them, all right? We add them. So meaning C1, C2 is going to be equal to 2 plus 4, which is going to give us 6 microfarad. 6 microfarad. Now this circuit reduces to this. The circuit reduces to this. So this is 2 microfarad. This is 3 microfarad. Now these two, we added them, so it became 6 microfarad. And then what else? The 4 microfarad. So now let's get the total capacitance. Now how do we do that? We follow the formula that says that what 1 over CT, or let's use resultant CR, which is the total, still the total capacitance, is equal to 1 over C1 plus 1 over C2 plus 1 over C3 plus 1 over C4. Now we have 1, 2, 3, 4 here. So it becomes 1 over CR is equal to 1 over, now the first one is 2 plus 1 over 3 plus 1 over 6 plus 1 over 4. Now, for us to add this together, we're going to find the LCM. So what's the LCM of 2, 3, 6, and 4? Actually, it should be 6, but let's check it out. All right, let's check that out. So this is 2, this is 3, this is 4, and then this is 6. So 2 goes here, 1, 2 here. You still have 3, this is 2, this is 3. Still use 2, this is 1, this is 2 and 3, that's 3. This is 1, this is still 3. So 3, so 3 here, we have 1, 1, 1. Now, so 2 times 2 times 3, that gives us 4. So the LCM of 2, 3, 6, 4 is not actually 6, but 12, all right? So the LCM of 2, 3, 6, and 4 is 12. So what does that become? It becomes 1 over CR is equal to 1. Now it becomes, put a dash here. Now what's the LCM between this? 12. 12 divided by 2 is 6. 6 multiplied by 1, that gives us 6. Plus 12 divided by 3, that gives us 4. 4 times 1, that gives us 4. Plus 12 divided by 6, that gives us 2. 2 times 1, that's 2. Plus 12 divided by 4, that gives us 3. 3 times 1, that's 3. So this is going to be 1 over CR is equal to, now 6 plus 4, that gives us 10. Plus 12, plus 2, that gives us 12. Plus 3, that gives us 15. So this is going to be 15 over 12. Now 3 can go in 15 here, and it's going to give us 5. 3 can go in 12 here, it's going to give us 4. All right, so we're going to be left with what? We're going to be left with, let's use here, let's manage this place to solve this. So we're going to be left with 1 over CR is equal to 5 over 4. So CR itself, now this is 1 over CR. For you to get CR itself, because the CR you are looking for, not 1 over CR, you inverse the right hand side. So CR becomes what? 4 over 5. So inverting this, you have 4 over 5. Now, of course, 4 over 5 is not in this option, but you can convert 4 over 5 to decimal. So what is going to be 4 over 5? 4 over 5 is going to be 0.8. Alright? But you don't just put 0.8. Yeah, I was supposed to put microfarad because all of them are in microfarad, or 0.8 microfarad. So the correct answer is 0.8 microfarad. You might be asking me, how do I convert fraction? How do I convert fraction to decimal? Now let's quickly do that. So this is 4 divided by 5. Now 4 divided by 5, of course, is not possible. Put your 0 point, put a 0 at the back of this 4. Now 40 divided by 5, that gives you 8. So you put your 8 here. 8 times 5, that gives you 40. 40 minus 40, that gives you 0. So 4 divided by 5 is 0.85. 0.85 microfarad is the resultant of these capacitors connected here. So the resultant capacitance in the figure below is 0.8 microfarad. If 8 times 10 to the power of minus 2 joules of work is required to move 100 microcoulomb of charge from a point X to a point Y in the electrical circuit, the potential difference between X and Y is, now take note, if 8 times 10 to the power of minus 2 joules of work, so this is work done. Now write your parameters down. So work done is given to you as 8 times 10 to the power of minus 2 joules. Is required to move 100 microcoulombs. 100 microcoulombs. That tells you that that is charge. Alright. So we are given that Q is equal to 100 microcoulombs. Now we're asked to find the potential difference between X and Y. Of course, we have to find V, which is the potential difference. And we have a formula that says W is equal to what? QV. Now to get V, we are going to make V the same formula. Divide both sides by Q. You have V is equal to what? W, alright, over Q. Alright, when you divide both sides by Q here, you have V is equal to W over Q. Now, so what is our work done? Our work done is given to us as 8 times 10 to the power of minus 2 over our charge is given to us as 100 microcoulombs. Do not forget your submultiple. Very, very important. Times 10 to the power of minus 6. Now, this 100 here, I can also write it as, so this is 8 times 10 to the power of minus 2. This 100, I can also write it as 10 to the power of 2 multiplied by 10 to the power of minus 6. Now, according to the law of indices, I can bring this together and it becomes 8 times 10 to the power of minus 2 over 10 to the power of, now you're adding this, so it becomes, add the powers, so it becomes minus 6 plus 2. Alright, so let's continue the journey from here. And then we're going to have what? Now, this becomes that V is equal to 8 times 10 to the power of minus 2 over, now that's going to be 10 to the power of minus 4. Now, we can bring this 10 to the power of minus 4 up here. But if we're bringing it up here, it becomes plus. Alright, so this is going to be equal to V is equal to 8 times 10 to the power of minus 2 multiplied by 10 to the power of minus 4. According to the law of indices, again, this is 8 times 10 to the power of, add their powers, minus 2 plus 4. So that gives us V is equal to 8 times 10 to the power of minus 2 plus 4. That gives us that gives us 2. Minus 2 plus 4, that gives us 2. So that gives us 8 times 10 to the power of 2 volts. 8 times 10 to the power of 2 volts. Now, this in the option, where is it? Where is the answer? Where is the answer? Where are we going to see it? Okay, so our answer is C. Alright, option C. 8.0, note, is still the same thing as 8. 8.0 is still the same thing as 8. So the potential difference between X and Y is 8.0 times 10 to the power of 2 volts. Two 15 microfarad parallel plate capacitors are connected in series. The combined capacitors is then connected across a 100-volt battery. The charge on each plate of the capacitor is, now, of course, you know that the same charge flow through the capacitors connected in series. So this is 50 microfarad, this is 50 microfarad, and they are connected across a 100 volts battery. So the same charge that flows here is the same charge that flows also through this capacitor. So we're asked to find the charge on each plate of the capacitor. Now, before we can find the charge, of course, Q is equal to CV. Now, we have to find the total capacitance of the capacitors. So now the total capacitance is going to be what? I told you that for two capacitors connected in series, we can use the formula C1 C2 over C1 plus C2. So that's going to be equal to what? 50 times 50 over 50 plus 50. Of course, 50 times 50, 5 times 5 gives us 25. The 0 and the 0 here gives us 0, 0, right? Over 50 plus 50, that gives us 100. Now this 0 takes away this 0, is going to be equal to 25 microfarad. Because don't forget, this is in micro. Do not forget that this is in micro. So this is going to be 25 microfarad. Now let's move on to finding the charge. So the charge is going to be equal to Q is going to be equal to CV. So the total capacitance is 25 microfarad. Do not forget your submultiple micro. So it's going to be 25 times 10 to the power of minus 6 multiplied by voltage 100, the total voltage. Now, it's going to be 25 times 10 to the power of minus 6 multiplied by, now 100 can be written as 100 to the power, 10 to the power of 2. Yeah, 100 can be written as 10 to the power of 2. According to the law of indices, we're going to bring this together. So Q becomes 25 times 10 to the power of minus 6 plus 2. So Q is equal to 25 times 10 to the power of minus 6 plus 2. That gives us minus 4 coulombs. Now, is any of our answer in this? We have this in our option. Now, we don't actually have it, but we have something close to this. Now, this is 25. This is 2.5 times 10 to the power of minus 3. Now, if I put a point between 2 and 5, this becomes 2.5 times 10 to the power of minus 3. Alright, this will reduce. Alright, it's like I'm adding 1 and then this point shifts here. Alright, if I take the points back, it becomes times 10 to the power of minus 1. With this, it becomes 10 to the power of minus 4. But if I move the point forward here, that's here, right, reversibly, it's going to become 10 to the power of minus 3 coulombs. So our answer is simply option B. So the charge on each plate of the capacitor is 2.5 times 10 to the power of minus 3 coulombs. Find the work done in moving a 2 coulombs charge between 2 points X and Y in an electric field. If the potential difference is 100 volts, find the work done. Of course, work done is equal to QV. So this is the formula we are going to use. So the work done is going to be equal to now 2 multiplied by 100. So that gives us what? 200 joules. Now let's see how our option is given here. Let's see how our option is given. It's actually given as 200 joules. So our answer is 200 joules. So the work done in moving a 2 coulombs charge between the 2 points X and Y in an electric field, if the potential difference is 100 volts, is 200 joules. A parallel plate capacitor has a common plate area of 5 times 10 to the power of minus 8 meters squared. So this is the area. So area is given to us as 5 times 10 to the power of minus 8 meters squared. And plate separation of 2 times 10 to the power of minus 3 meter. Plate separation, that's the distance between the plates, is 2 times 10 to the power of minus 3 meter. Assuming free space, what is the capacitance? Now we're given these options and then we're given E0, which is the permittivity of free space. Permittivity of free space. E0 is the permittivity of free space. And it has a constant value of 9 times 10 to the power of 10 to the power of minus 12 coulomb squared per Newton meter squared. So now, what formula do we apply here? We have E0 to be this. Now, we apply the formula that says capacitance is equal to E0 A over D. Where A is the area, of course, you know E0 is the permittivity of free space, and then D is the distance between the plates. Alright, so to find the capacitance, we use this formula. So C is going to be equal to E0, which is 9 times 10 to the power of minus 12 multiplied by your area, That's 2 times 10 to the power of minus 3 over your distance. Now, also, sorry, this is not the area. The area is 5 times 10 to the power of minus 8 over the distance. 2 times 10 to the power of minus 3. Now, how do we go about this? How do we go about this? Now, this is 9 times 5. And 9 times 5 is going to give us what? 85, because 8 times 5, sorry, gives us 40. 8 times 5 gives us 40. So 9 times 5 is going to give us 45. 45. So 9 times 5 gives us 45. So this becomes 45 multiplied by, now, this is 10 to the power of minus 12. We're going to add it to this because this is, according to law of integers, this is 10, this is 10. So we're going to add their power. So it's going to be plus into bracket minus 8. Of course, you know plus times minus gives us minus. So it's just going to be minus 12 minus 8. Minus 12 minus 8 over 2 times 10 to the power of minus 3. Now let's take this further. So this becomes that C is equal to minus 12 minus 8. That gives us minus 20. So this is going to be 45 times 10 to the power of minus 12 minus 8. That gives us minus 20 over 2 times 10 to the power of minus 3. Now minus 3 can come up here, but for it to come up here, it becomes plus. So it becomes C is equal to 45 times 10 to the power of minus 20 plus minus 3. Alright? Sorry, multiplied by 10 to the power of 3 over 2. So this is going to be equal to, now this and this are the same, so add their power. So it becomes 45 times 10 to the power of minus 20 plus 3 over 2. So minus 20 plus 3, of course, gives you minus 17. So this is going to be C is equal to, I have to make space for this. I have to make space. Where do I make the space? Where do I make the space? Let me make it here. Let me make it here. So now, capacitance is equal to minus 20 plus 3. That gives you 45 times 10 to the power of minus 17 over 2. Now, of course, 45 divided by 2 gives you what? 45 divided by 2 gives you what? Now, 2 in 40 gives us 20. 2 in 5 gives us 2.5. So that's going to be what? 22.5. So C is going to be equal to 22.5 multiplied by 10 to the power of minus 17. What's the unit for capacitance? Farad. Right? So 22.5 times 10 to the power of minus 17 farad. Now, which of these options is looking like this? Which of these options looks like this? Which of the options look like this? Now, this is going to be, now, which of these options looks like this? Now, this is 2.25 times 10 to the power of, times 10 to the power of 7, and this is, alright, see that they did not write this well. Okay, alright, this is actually to the power of minus 16, sorry. And then also this is actually, okay, this is to the power of minus 17, this is power of minus 16. Yes, and then this also is to the power of minus 17. That's according to the option here. So, because it's about to confuse me and I'm like, what the heck? So we have 22.5 times 10 to the power of minus 17. So now this is 2.25 times 10 to the power of minus 16. If I shift this forward, alright, if I shift this forward, this is going to reduce by 1. So this becomes C is equal to 2.25 times 10 to the power of minus 16 farad. So option C is our answer. Alright, so that's the answer to this question. 2.25 times 10 to the power of minus 16 farad. In the circuit above, the potential across each capacitor is 100 volts. The total energy stored in the two capacitors is, now look at these capacitors, they are connected across each other, meaning they are connected in parallel. So their total capacitance is going to be what? It's It's going to be 2 plus 3. That gives us 5 microfarad because they are both in microfarad. And the voltage flowing across them is 100 volts. So now the total energy stored, do not forget, is half CV squared or half QV, but let's use this. So E is going to be equal to half multiplied by 5, all right, times 10 to the power of minus 6. Okay, let me make space for this. So this is going to be equal to half multiplied by 5 times 10 to the power of minus 6. Your micro, don't forget to submultiply, multiplied by V squared. That's 100 squared. All right. So this is going to be what? This is going to be, let's continue from here. This is going to be E is equal to 1 over 2. Now, let's do this. Let's treat this together. So this is going to be 5 over 2. That's 1 over 2 multiplied by 5. That's 5 over 2 multiplied by 10 to the power of minus 6 multiplied by. Now, 100 can also be written as 10 to the power of 2. Now, and there's a power outside. So according to the law of indices, 2 times 2, that becomes what? 4. So E is equal to what? 5 divided by 2, of course, gives us 2.5 times 10 to the power of minus 6 multiplied by 10 to the power of 4. Now, we're going to add their powers. So adding their powers, that's coming here, this becomes E is equal to 2.5 times 10 to the power of minus 6 plus 4. So that gives us E is equal to 2.5 times 10 to the power of minus 6 plus 4. That gives us minus 2 joules. 2.5 times 10 to the power of minus 2 joules, which is option C. So this is our answer, 2.5 times 10 to the power of minus 2 joules. The diagram shows two capacitors P and Q of capacitances 5 microfarad and 10 microfarad. Find the charges stored in P and Q respectively. Find the charges stored in P and Q respectively. Find the charges stored in P and Q respectively. So let's go straight to business. Now, of course, these capacitors are connected in parallel. So different charges flows through them. The charge that flows through here is not the same charge that flows through here. All right. So let's find the charge stored in P and Q. Now, what's the formula for charge? Charge is CV. Q is equal to CV. Of course, the same voltage flows through them. Yeah, the same voltage flows through them. So what's going to happen is that this becomes, now let's find for P. For P, Q is going to be equal to, that's QP is going to be equal to CP, which is 5 microfarad. That's 5 times 10 to the power of minus 6 multiplied by the voltage 20. All right. So this becomes what? This becomes QP is equal to, now 5 times 20, of course, gives us what? 100. Gives us 100. Because 5 times 2 gives us 10. With the 0 in the 20, that gives us 100. Times 10 to the power of minus 6. So this is 10 times 10 to the power of minus 6. Don't forget, is micro. So QP is going to be equal to 100 microcoulombs. So for P, we have 100 microcoulombs. Now, let's go to the other one. Now, the answer should be option C, sir. Because they said P and Q respectively, all right? P and Q respectively. So the answer is already C. But let's solve it. Let's solve it. So for Q, that's for QQ, that's Q sub Q. Let's just put it like that. It's going to be what? 10 microfarad. That's 10 times 10 to the power of minus 6 multiplied by 20. So 10 times 20, that gives us 200 times 10 to the power of minus 6. 10 to the power of minus 6 micro. So that's going to be 200 microcoulombs. Like I said, see? So the charges stored in P and Q respectively are simply 100 microcoulombs and 200 microcoulombs. A piece of rectangular glass block is inserted between two parallel plate capacitors at constant plate area and distance of separation. The capacitance of the capacitor will remain when a piece of rectangular glass block is inserted between two now, what is this rectangular glass block doing here? It's actually the dielectric material, and I told you that the dielectric material separates the two plates, also increases the capacitance by reducing the electric field, all right, between the two plates. So it is simply, when you have this case at constant plate area and distance of separation, the capacitance of the capacitor will increase. So option D is our answer. Increase. The diagram shows three capacitors C1, C2 and C3 of capacitors 2 microfarad, 6 microfarad, 3 microfarad respectively. The potential differences across C1, C2 and C3 respectively are, now these capacitors are connected in series and then this voltage that's flowing across them 12 volts. Now before we can find the potential difference across each capacitors, we have to find the charge. Don't forget that Q is equal to CV. So you will need the charge to be able to find, you already have the capacitors or the capacitance, right? Or the capacitors here. You will need to find the charge. You already have the voltage. You need to find the charge. All right. Very, very important. So now Q is going to be equal to what? Now, before we can find Q, we have to find the total capacitance. So it becomes that 1 over CT is equal to 1 over 2 plus 1 over 6 plus 1 over 3. Now, the LCM of 2, 6 and 3, of course, is 6. So this is going to be 1 over CT is equal to, the LCM is 6. 6 divided by 2 gives us 3. 3 times 1, 3. Plus 6 divided by 6 gives us 1. 1 times 1 gives us 1. Plus 6 divided by 3, that gives us 2. 2 times 1, that gives us 2. So this is 3 plus 1 plus 2. That gives us 1 over CT is equal to 6 over 6. So this is 1 over CT is equal to 6 divided by 6 is 1. Now, if you cross multiply, alright, you're going to have CT is equal to 1. 1 what? 1 microfarad. So the total capacitance here is 1 microfarad. Now, let's get the charge. So charge is going to be equal to what? 1 times 10 to the power of minus 6 multiplied by the total voltage, 12 volts. Right, so this is going to be what? Q is equal to what? 12 micro, that's microcoulombs. 12 microcoulombs is the charge. So this is the total charge, and the total charge is still the same charge flowing through this capacitor, flowing through this capacitor, flowing through this capacitor. So now we can find the voltage on each capacitors. We can find the voltage on each capacitors. So following the same formula, now V1 now is going to be equal to what? V1 is going to make V the sort of formula here, divide both sides by what? C. It's going to be Q over C1, right? So that's going to be equal to what? Q, that's 12 microcoulombs, right? Divided by C1 is 2 microfarad, right? So micro takes away micro, and then 12 divided by 2, we have 6. So this is going to be 6 volts. Now V2 is going to be equal to Q over C2. So this is going to be equal to 12 microfarad coulombs, over what? 6 microfarad. So this is 6 microfarad. So micro takes away micro. 12 divided by 6, of course, gives you 2 volts. Now let's get V3. That's the voltage flowing across the third capacitor, C3. So now this is going to be 12 microcoulombs over 3 microfarad. So micro takes away micro. 12 divided by 3, that's you have 4 volts. Right, now check very closely. If you add 6 plus 2, that gives you 8. 8 plus 4, that gives you 12. 12 volts, meaning that this concept is very correct. So the voltage or the potential differences across C1, C2 and C3 are respectively 6 volts, 2 volts and 4 volts. So option A gives us our correct answer. 6 volts, 2 volts and 4 volts. The diagram shows two capacitors P and Q, capacitance 2 and capacitance 2 microfarad and 4 microfarad respectively, connected to a DC source 20 volts. The ratio of energy stored in P to Q is the ratio of energy stored in P to Q. Now we'll have to find the energy for P and we'll have to find the energy for Q. Energy stored in P and energy stored in Q. Now energy stored, alright, is half CV squared. So energy stored in P is going to be equal to half multiplied by 5 times 10 to the power of what? Minus 6 micro, do not forget, times 20 to the power of 2. So this is going to become what? 1 over, that's okay, 1 times, so that's 5 over 2 multiplied by 10 to the power of minus 6 multiplied by, now 20 to the power of 2 is 20 times 20, which gives us what? 400. All right, gives us what? 400. So now this becomes, now 2 goes here, 1, 2 can go here, that's 2, so we have 200 here. So we have 5 times 200. So what's that going to give us? 0, 0, 10. That's going to give us 1000. 5 times 200, because 2 here, 1, 2 here, 2. So 5 times 200 that's left here is going to give us 1000 times 10 to the power of minus 6. Times 10 to the power of minus 6. Right? So this becomes, now this can be written as 10 to the power of, this can be written as 10 to the power of 3. So this is 10 to the power of 3 multiplied by 10 to the power of minus 6. Now add their powers, it becomes 10 to the power of 3 plus minus 6. But this is going to become minus 6. Plus times minus, that gives you minus. So 3 minus 6, that gives you 10 to the power of minus 3 joules. 10 to the power of minus 3 joules. Now let's get the energy stored in capacitor Q. Let's get for Q. So EQ is going to be equal to half multiplied by 10 times 10 to the power of minus 6 multiplied by 20 squared. So this is going to be 2 here, 1, 2 here, 5. So this is going to be, EQ is going to be equal to 5 times 10 to the power of minus 6 multiplied by 20 to the power of 2 gives us what? 400. Alright, so 5 times 4 gives us 20. Then with the 2 zeros, that becomes what? 0, 0. That is 2000. 5 times 4 gives us 20. Then these 2 zeros at the back here times 10 to the power of minus 6. Now, this can also be written as 2 times 10 to the power of 3. That's 2000 can also be written as 2 times 10 to the power of 3 EQ. So we don't confuse this. So 2 times 10 to the power of 3 multiplied by 10 to the power of minus 6. So add their powers, you have what? EQ is going to be equal to 2 times 10 to the power of minus 3. Sorry, 3 plus minus 6, of course, going to give us minus 6. So it's going to be equal to what? 2 times 10 to the power of 3 minus 6. That gives us minus 3 joules. Alright, so we have 10 to the power of minus 3 joules here, and we have times 2 times 10 to the power of minus 3 joules. And we are asked to find the ratio of energy stored in P to Q. So the ratio of energy stored in P to Q, that's EP divided by EQ, is going to be equal to what? 10 to the power of minus 3 here over 2 times 10 to the power of minus 3. Now this takes away this. So you have 1. You have 10 to the power of minus 3 here, 1. 10 to the power of minus 3 here, 1. So you're going to be left with 1 over 2. Which is the same thing as saying that what? That the ratio from here, the ratio of energy stored in P to the ratio of energy stored in Q is going to be equivalent to 1:2. 1:2, because you have 1 over 2. 1 over 2 can also be written as 1:2. So this is your answer, which is option A. So option A is our answer. 1:2 is the ratio of energy stored in P to Q. The energy stored in a capacitor of capacitance 10 microfarad carrying a charge of 100 microcoulombs is, now we are given capacitance as 10 microfarad and we are given the charge as 100 microcoulombs, and we are asked to find the energy stored. Now energy stored in a capacitor is half CV squared, but we don't have the voltage, we don't have the or what is called, or which can also be called, the potential difference. So how do we solve this? Now don't forget that I told you too that energy stored in a capacitor is also half QV. Now this formula also has voltage, which is also called potential difference. So how can we find the energy stored here without the voltage? How is that possible? Like, how? Yes, we can find it. Now remember that Q is equal to CV. Now make V the same formula from here. V is going to be equal to Q over C. So meaning that V is the same thing as Q over C. So I can replace V here as Q over C. So E becomes 1/2 multiplied by Q multiplied by V, which is Q over C. So multiply together, you have E is equal to 1 times Q times Q, that gives you Q squared, over 2 times C, that gives you 2C. All right, so this is the energy stored formula that we can use to solve this question. Now let's move further to solving it. So this becomes E is equal to Q squared, that's 100 microcoulombs squared, so 100 times 10 to the power of minus 6 squared over 2 multiplied by the capacitance, which is given us as 10 times 10 to the power of minus 6 micro, the sum multiple. So this is going to be E is equal to 100 can be written as 10 to the power of 2 times 10 to the power of minus 6 all to the power of 2 over 2 times, now this is to the power of 1, this 10 is to the power of 1 here, this 10 is to the power of 1, 10 to the power of 1 is still 10, so I'm going to add their powers. It becomes 10 to the power of minus 6 plus 1, so this becomes E is equal to, now adding this power 2 because of the law of indices becomes, now this 2 plus minus 6, that's going to be minus 6 plus 2 over 2 times 10 to the power all squared, do not forget. Now minus 6 plus 1, that gives us what? Minus 5. Minus 5. Now let's continue. Minus 6 plus 2, that gives us minus 4. So this is going to be 10 to the power of minus 4 all to the power of 2 over, this is going to be 2 times 10 to the power of minus 5. Now minus 4 times 2, that gives us what? Minus 8. So this is going to become 10 to the power of minus 8. According to law of indices, you can multiply this and they open, so it becomes 2 times 10 to the power of minus 5. Now 10 to the power of minus 5 can go up here, but when it goes up it becomes positive. So let's continue from here. So we're going to have it to be E is equal to 10 to the power of minus 8 times 10 to the power of 5, positive 5, because this is going up, over 2. So this is going to become, now we're going to add the powers, it becomes 10 to the power of minus 8 plus 5 over 2. This becomes E is equal to 10 to the power of minus 8 plus 5, that gives us minus 3 over 2. Now I can split this to be 1 over 2 multiplied by 10 to the power of minus 3. Because 1 times 10 to the power of minus 3 is still 10 to the power of minus 3 divided by 2. So let's continue. I have to rub off the board. Where do I rub off? Okay, let me rub off this side. This side. Let me give the options. Now, so let's continue. Now, 1 over 2 can also be written as 0.5. That's converting 1 over 2 as a fraction to decimal, you get 0.5 times 10 to the power of minus 3 joules. Now, you're not seeing, are you seeing anything like 0.5 here? No, you are not, probably. But we see something like 5. There's 5 here, there's 5 here. This is to the power of 4. So there's 5 here, there's 5 here. So how do we go about this? Now, if I move this point forward, it becomes what? 5 times 10 to the power of minus 1 multiplied by 10 to the power of minus 3. Bring this and this together. That means we're going to add the powers. It becomes 5 times 10 to the power of minus 4 joules. So this is going to be our answer, 5 times 10 to the power of minus 4, which is option D. So that's the correct answer to our question. 5 times 10 to the power of minus 4 joules. Given 3 capacitors, 0.3 microfarad, 0.5 microfarad, and 0.2 microfarad are joined. The minimum capacitance is, now they're trying to ask you, how will you connect these capacitors to get the least capacitance? Now, when you combine capacitors or when you connect capacitors in series, you have minimum capacitance. Now, don't forget that when you are trying to find the total capacitance, when capacitors are connected in parallel, you add them. So that is meaning that when you connect them in parallel, you are increasing the capacitance. But when you connect them in series, you are going to be reducing the capacitance. All right, you're going to get the minimum capacitance. So meaning that we have to combine this in series to get the minimum capacitance. So when we combine it in series, what are we going to get? Now this is going to be, let me draw a diagram. So we have 0.3 microfarad, we have 0.5 microfarad, and then we have 0.2 microfarad. So the minimum capacitance is, now let's combine them together. Now of course we're going to use the formula 1 over Ct is equal to 1 over C1 plus 1 over C2 plus 1 over C3. So it becomes 1 over Ct is equal to 1 over 0.3 plus 1 over 0.5 plus 1 over 0.2. Now 0.3, let me bring you in mind that this now can be converted to fraction. Just take this here, it becomes 3 over, this is 1, then how many times did you count? Once. Put your 0. Now meaning that 0.3 is 3 over 10. So this is going to become 1 over ct is equal to 1 over 3 over 10. Now meaning that 0.5 itself also is going to be 5 over 10. That's going to be 1 over 5 over 10. Plus this also is going to be 1 over 0.2. It can also be written as 2 over 10. Now, you are seeing inverse of 3 over 10, inverse of 5 over 10, inverse of 2 over 10. Now, what does that mean? So, the inverse of 3 over 10 here is going to be what? 10 over 3. Now, the inverse of 5 over 10 here is going to be, because you are seeing 1 over, so it's going to be what? 10 divided by 5. Plus, do this the same here. It's going to be 1 over 10 divided, sorry, it's going to be 1 over, it's going to be 10 divided by 2. That's what we're going to have there. So, now, from here, we're going to have 1 over ct is equal to 10 over 3 plus 10 divided by 5, that gives us 2, plus 10 divided by 2, that gives us 5. 2 plus 5, that gives us 7. So from here, we're going to have 1 over ct is equal to, it's going to be 10 over 3 plus what? 7. Now let's find the LCM. LCM of 3 and 1 is 3. That's 1 over ct is equal to 3. 3 divided by 3, 1. 1 times 10, 10. Plus 3 divided by 1, 3. 3 times 7, 21. So this is going to be 1 over ct is equal to 31 over 3. Now to get ct, you are going to inverse. Alright, so ct is going to be equal to, that's the total capacitance. It's going to be 3 over 31. Now divide that, you're going to have 0.097 microfarad. Now is there anything like this here in the option? No. We can approximate this 9 to this 0. We can give it 1 to 1 decimal place. So if you take 1 from here to down here, it becomes 0.1 microfarad, which gives us option C. So this is going to be our answer to the option. 0.1 microfarad is the minimum capacitance when these are joined in series. The figure shows the capacitors 2 microfarad, 3 microfarad, and 6 microfarad connected in series. If the PD across the system is 12 volts, the PD across the 6 microfarad is, now you know that in series connection of capacitors, charge is constant. That means the charge that flows through here is the same charge that flows through here that flows through here, but the voltage is not constant. The voltage flowing through here are different. So this is actually V1, V2, and V3. So they have different voltage flowing through them. So we are asked to find the PD across the 6 microfarad. Now, how do we do that? Before we can do that, now, remember that Q is equal to CV, alright? So meaning that V is equal to Q over C. Now, so you need your charge and the capacitance, which you already have, to find the potential difference across the 6 microfarad capacitor. So now we have to find the charge. So how do we do that? Before we can find the charge, we need to find the total capacitance. All right, before we can find the we can find the PD across the 6 microfarad, we have to find the charge. So let's do that. How do we do that? We have to get the total capacitance first. Right, we have to get the total capacitance first. So it becomes what? 1 over ct is equal to 1 over c1, which is going to be 2 plus 1 over 3 plus 1 over 6. So this is going to be 1 over ct is equal to SM of 2, 3, and 6 is 6. 6 divided by 2 gives us 3. 3 times 1, 3, plus 6 divided by 3 gives us 2. 2 times 1, 2, plus 6 divided by 6 gives us 1. 1 times 1, that's 1. 2 plus 3 plus 1, that gives us 6. So we have 1 over ct is equal to 6 over 6. Now, meaning that 1 over ct is equal to 1. Now, cross multiply, you're going to have ct is equal to 1 microfarad. 1 microfarad. So let's get the total charge now. So the total charge is going to be Q is equal to 1 microfarad, 1 times 10 to the power of minus 6, multiplied by the total voltage, 12, right? The total voltage. Yeah, we're working with total capacitance and the total voltage. So now this is going to be times 12. So this is going to be Q is equal to 12 times 10 to the power of minus 6 coulombs, which is 12 microcoulombs. So now we can now find the voltage across the 6 microfarad. So that means V3 now is going to be equal to, coming back here now to find the voltage across this, or the PD across this, it becomes what? Q, which is the charge, 12 times 10 to the power of minus 6, which is constant, over now the capacitance, which is 6, not just 6 times 10 to the power of minus 6, because you have 6 microfarad. So this takes this away, you're left with 12 divided by 6, you're left with what? 2. So 2 volts is our answer. So the voltage flowing through this is 2 volts. So our answer here is 2 volts. If the capacitance of a capacitor is C, which of the following parameter varied when variable capacitor is used for turning radio sets? Now you're asking, when you use a capacitor, if the capacitance of a capacitor is C, which of the following parameter varied when variable capacitor is used for turning radio sets? Which of them is varied? Now they said constant E naught and area, B area and distance, C constant E naught only, D distance only. Now how do we go about this? This E naught constant is the permittivity of free space, alright? So now there's a formula that we know that capacitance is equal to E naught A over D. Now it means that, don't forget, E naught is constant. It means that the capacitance is directly proportional to the area and inversely proportional to the distance. So what will be varied here will be the distance. Alright, what will be varied here will be the distance. So the only thing that will be varied will be the distance only. So distance only is the correct answer to this question. The capacitance of a parallel plate capacitor when in air is 2 microfarad and in the presence of a dielectric material 6 microfarad. The dielectric constant is, now straight to the point, is either you use the formula C1 over K1 is equal to C2 over K2, or you use the formula K is C over C naught. Now this is when this is the capacitance in the dielectric material and this is the capacitance in air. Alright, so is that we use this or we use this? Now let's use this. Now what will be our K1? Because here we'll be looking for K2. Our K1 is going to be our dielectric constant in air, which is going to be equal to 1. Right, so this becomes C1. Alright, our C1 here is what? 2 microfarad and our C2 is 6 microfarad. So this becomes 2 alright, 2 times 10 to the power of minus 6 over K1, which is 1, is equal to C2, 6 times 10 to the power of minus 6 over K2, which we are looking for. So cross multiply, you're going to have 2 times 10 to the power of minus 6 K2 is equal to 6 times 10 to the power of minus 6. Now from here this can take this away, right? So divide both sides by 2. Now you are going to have K2 is going to be equal to 6 divided by 2, which is going to be equal to 3. So our answer is 3. Or if you decide to use this formula, you're still going to get the same thing. K is going to be equal to your capacitance in the dielectric medium, which is 6 microfarad, over the capacitance in air. So that's going to be 3 times, or sorry, that's 2 times 10 to the power of minus 6. This takes this away, 6 divided by 2, 3. So K is equal to 3. So you're still going to get 3. So any of these formulas you can use. So our answer here is 3. If 2 charge plates are maintained at a potential difference of 3 kilovolts, the work done in taking a charge of 600 microcoulomb across the field is, potential difference is given to us as 3 kilovolts and a charge of 600 microcoulombs is given to us. So we have V is equal to 3 kilovolts, which is the same thing as 3 times 10 to the power of 3 volts. This 10 to the power of 3 is kilo. Alright, 10 to the power of 3 is also 1000. Do you understand? So 1000. So now, you know, some persons just say, send me 5k. They don't really know that I've met some persons, they don't really know that the k there is 1000. Alright, so when you say send me your gen 2k, So he actually may send me urgent 2,000 naira. All right. So let's continue. So now we are giving the charge as 600 microcoulombs, which is 600 times 10 to the power of minus 6 coulombs. So we want to get the work done. Now we know that W is equal to QV. All right. So this is the formula to get the work done. All right. So W is going to be equal to Q, which is what? 600 times 10 to the power of minus 6 multiplied by 3 times 10 to the power of 3. Now 6 times 3 is 18. So this is going to be 18 times, now these two zeros can be written as 10 to the power of 2 times 10 to the power of minus 6 that was here times 10 to the power of 3. That's these two zeros here. I multiply 6 and 3, 18. All right. These two zeros are like 100. They can be written as 10 to the power of 2. So now let's do our indices. So this is going to be 18 times 10 to the power of, add it. It's going to be minus 2 minus 6 plus 3. So that's going to be W is equal to 18 times 10 to the power of 2 minus 6. That gives us what? Minus 4 plus 3. So this is going to be W is equal to 18 times 10 to the power of minus 4 plus 3. That gives us minus 1. So that gives us 8 times 10 to the power of minus 1 joules. Now I want you to know that this is 18 times 10 to the power of minus 1, right? I want you to know that 10 to the power of minus 1 can also be written as 1 over 10. So this is going to be W is equal to 18 over 10. Now, this 18 dividing this 10 now can now make it become 1.8 joules. If it was 18 over 100, it would have been 0.18 because this point move here at 10, then the other point that becomes this. All right. I want you to understand this. So, but the actual thing is that 18 divided by 10, it moves this point for here, all right, backwards. So you have 1.8 joules. So 1.8 joules is our answer, which is option D. So option D is our answer. So 1.8 joules gives us the work done in taking a charge of this across the field. 3 capacitors of capacitance 2 microfarad, 4 microfarad, and 8 microfarad are connected in parallel, and a PD of 6 volts is maintained across the capacitor. The total energy stored is, so we have that the capacitors are connected in parallel. So this is, let me just draw a diagram to illustrate this. And they are connected across a PD of 6 volts. So this is 6 volts. This is 2 microfarad, 4 microfarad, and 8 microfarad. So now we're asked to find the total energy stored. We have to get the total capacitance before we can find the total energy stored. Let's get the total capacitance. So it becomes what? That the total capacitance now becomes CT is going to be equal to, they are connected in parallel, so we add them. So it becomes 2 plus 4 plus 8. 2 plus 4, 6, right? 6 plus 8, that gives us 14. So that's going to be CT is equal to 14 microfarad. So this is the total capacitance. Now we can get the energy stored. Energy stored is half CV squared. So that becomes E is equal to half multiplied by 14 times 10 to the power of minus 6. Don't forget, micro, multiplied by V squared, which is 6 squared. So now, if you notice, 2 is here. This is 14. So 2 can go here 1. 2 in 14. We're going to be left with 7. Let's continue from here. So we're going to have E is equal to 7 times 10 to the power of minus 6 multiplied by, now 6 squared gives us what? 36. Alright, 6 squared gives us 36. 6 squared gives us 36. So we are going to multiply 7 times 36, right? 36 multiplied by 7. 36 multiplied by 7. So 36, 7 times 6, that gives us what? 42. So that's 2 carry 4. 7 times 3, 21, plus 4, that's 25. That's 252. All right, that gives us 252. So this is going to be 252. So 7 times 36 gives us 252 times 10 to the power of minus 6 joules. Now, do we have anything like this in our option? Do we have anything like this? This is 2.52 times 10 to the power, which is not the same thing as this, but let's look at this. Let's look at this. Now, if we move this forward 1, 2, we're going to have times 10 to the power of minus 2. Combining with this, you have 10 to the power of minus 6. Meaning also that if we move this 0.1, 2, this is going to reduce by 2. Alright, so E is going to be equal to 2.52 times 10 to the power of minus 4 joules. Alright, so that's option A. So this is our answer. So our answer is 2.52 times 10 to the power of minus 4 joules. Is total energy stored. The capacitance of a parallel plate capacitor is 20 microfarad in air. In air. Alright, that C0 is 20 microfarad in air. And 60 microfarad in the presence of a dielectric. What is the dielectric constant? Now this is the capacitance in the presence of a dielectric, 60 microfarad. Now, straight to the point. Simply use K is equal to C over C0. This is the capacitance in the dielectric material or medium, and then this is the capacitance in air. So K is going to be equal to, so this is equal to 60 times 10 to the power of minus 6 over 20 times 10 to the power of minus 6. Now, of course, this takes this away. So 0 cancels 0, 6 divided by 2, you have 3. So K is equal to 3. So our answer is option C, 3.0. Capacitors are used in the induction coil to prevent electric sparks, B, prevent distortion of electric fields, C, control circuits, D, dissipate energy. Capacitors are used in induction coil. Now, what's an induction coil first before we go to the capacitors? An induction coil is a device that produces high voltage, all right, when electric currents flow through it. So now, and we are talking about capacitors. Now, what are capacitors? What does a capacitor do? A capacitor is a device that stores electrical energy or electric charge. It is used for fluctuation also in electronic circuits. It is used for circuit filtering and so on and so forth. Now, the only thing that it is used to do here, it is to prevent electric sparks. So capacitors are used in induction coil to prevent electric sparks. So that's the answer, to prevent electric sparks. What charge is stored in a 0.1 farad capacitor when a 10 volt supply is connected across it? What charge is stored? Now, charge is equal to CV. Now we are giving the capacitance 0.1, so this is equal to 0.1 multiplied by the voltage 10. Now this 0.1, when it's multiplied by 10, it moves this point forward, so it becomes 1. So Q is equal to 1 coulombs. So option A is our answer. Calculate the effective capacitance of the circuits above. That's the circuit here. Now this is 2 microfarad, 2 microfarad, 2 microfarad, 2 microfarad, 3 microfarad. Now if you notice, these three are connected in parallel because they are connected across each other, across each other, across each other, across each other. So they are connected in parallel. So we are going to combine them first. When we combine them, then we can move further. So now let's combine them. So combining this in parallel, so it becomes what? So let's say this is C1, this is C2, this is C3, and then this is C4, and probably this is C5. So C1, 2, 3 is going to be, that's adding all of these, 2 plus 2 plus 2. That gives us what? 6 microfarad. Now, having combined this, now this circuit resolves to become this. It now becomes this. Alright, so your circuit becomes this. You have your 2 microfarad here. Now you combine this, you have your 6 microfarad here. And then you have your 3 microfarad here. Now, as they are like this, they are connected in series. Don't think that these two now are connected in parallel. No, it's just like a wire that was straight, but it became bent. Maybe the capacitors were connected end to end and then they bent it. It's still series, all right? So if you open it like this, if you straighten it, just try to use your imagination with me. I'm not with a wire here, if not I would have shown you, all right? So I think, okay, this is one. Yeah. So it's just like a straightened wire like this, all right? So it was bent like this. It's still in series, all right, because they are connected end to end, end to end. So if you bend it like this, they are still connected in series. So now these three are in series, so we're going to resolve them now and get the effective capacitance, which is the total capacitance. So it becomes 1 over Ct is equal to 1 over 2 plus 1 over 6 plus 1 over 3. Now the LCM of 2, 6 and 3 of course is 6. So it's going to be 1 over Ct is equal to, this is 6. 6 divided by 2 gives us 3. 3 times 1, 3. Plus 6 divided by 6 gives us 1. 1 times 1, 1. Plus 6 divided by 3 gives us 2. 2 times 1, that's 2. So 3 plus 1, 4 plus 2, that's 6. So this is 1 over Ct is equal to 6 over 6. Now that gives us 1. Let's continue from here. Let's continue from here. So it becomes 1 over Ct is equal to 1. Now, if you cross multiply, you're going to have Ct is equal to 1 microfarad. 1 microfarad. So our answer is option B, 1 microfarad. So this gives us the effective capacitance of the circuit. The plates of a 0.5 microfarad uncharged capacitor are connected to a 10 volt battery. The charge on the capacitor after a long time is, now charge, that's Q, is CV. So this is simply going to be, the capacitor is 0.5, although we have micro, that's times 10 to the power of minus 6 multiplied by the voltage 10. Now just know that this 10 here, you can shift this point forward, so you are going to be left with 5. So Q is going to be equal to 5 times 10 to the power of minus 6 coulombs, and 10 to the power of minus 6 is micro. That gives you 5 micro coulombs. So this is the charge. So we have 5 micro coulombs. So meaning that option D gives us our answer, 5.0 microcoulombs. From the diagram above, the equivalent capacitance of the three capacitors is, now these capacitors are connected in series. Of course, it becomes 1 over Ct is equal to 1 over 3 plus 1 over 3 plus 1 over 3. Of course, this is 1 over 3 in 3 places, so it's still the same thing as writing 1 over Ct is equivalent to writing the same thing as 3 times 1 over 3. The 3 takes away 3 here, you are left with 1. So this is going to be 1 over Ct is equal to 1. Alright, so when you cross multiply, you're going to have Ct is equal to 1 microfarad. So our answer is option C, 1 microfarad. When a capacitor is charged to 20 coulombs on each plate, the energy stored by it is 40 joules. At what charge will it store half of this energy? Now, just hold on here. Before we go and answer this question, let's hold on here. We have charge given to us at 20 coulombs, and then we also have the energy given to us as 40 joules. So it now says at what charge will it store half of this energy? Half of this energy. Now, before we can find at the charge at which it will store half of this energy, we have to find voltage. Now, E is equal to half CV squared. But in this case, we don't have anything like C. So we're going to use E is equal to half QV. Don't forget this formula, half QV. So now we can get V from here. So making V the substitute formula, I can also write this as E is equal to QV over 2. So this is over 1. Let's cross multiply. So this multiplies, okay, this multiplies this. You have QV times 1, that gives you QV is equal to E times 2, that gives you 2E. So meaning that V is going to be equal to 2E over, by the time you divide both sides by Q over Q. So V is going to be equal to 2 times E is 40 over Q is 20. So we have 0 cancel 0 here. This 2 takes 2 away from here. We're left with 4. So we have 4 volts. Alright. Now that we have the voltage, we can now find the charge at which it will store half of this energy. So they're saying at what charge? Now this is the first instance. The voltage was 4 volts, the charge was 20 coulombs, and the energy stored was 40 joules. Now at the second case, now they're not saying at what charge will it store half of this energy. So what charge will it store half of this energy, 40? At what charge will it store half of this energy? That's half of 40. So our energy in this case is going to be half of 40, which is going to be equal to 20 joules. So at what charge? So Q is going to be equal to what? Now, which formula are we going to use? We can use Q is equal to CV. We have our energy here. So we're going to use E is equal to what? Half, which is energy, half QV. Alright. Now, we're actually looking for the charge. So we're going to make charge something formula here now. So you can also write this E as QV over 2. Cross multiply, you're going to have QV is equal to 2E. To make you the simple formula, you're going to have 2E over V. Right? 2E over V. So now let's find the charge now. So the charge now is going to be equal to 2 times the energy stored is 20 over V, which is 4. Now 4 go here 1, 4 here 5. So 2 times 5, that gives us 10. So Q is equal to 10 coulombs. So this will be the charge. Okay, this will be the charge when half of this energy is stored. So option A is our answer, 10 coulombs. From the diagram, calculate the energy stored in the capacitor. Now we have 8 microfarad capacitor here, and we have the voltage or the potential difference across it to be 10 volts. And we have to calculate the energy stored. Now, of course, energy stored is half CV squared. So it's going to be equal to 1 over 2 multiplied by the capacitance or the capacitor is 8 microfarad. That's 8 times 10 to the power of minus 6 multiplied by V squared. That's 10 squared. 10 squared. So now this is going to be E is equal to, now 2 can go here 1, 2 can go here 4. So you're left with 4 times 10 to the power of, bring this together, you have minus 6 plus 2 because it's multiplication that is between them. So this becomes E is equal to 4 times 10 to the power of minus 6 plus 2, that gives us minus 4. That's 4 times 10 to the power of minus 4 joules. So this is our answer, which is option B. So that will be our answer. The dielectric of a capacitor is used to is it balance up the energy, regulate the current flow, boost the voltage between the plates, or increase the energy stored. Now, it does not increase the energy stored. Dielectric in a capacitor does not increase the energy stored. It does not even boost the voltage between the plates. If it's even boosting anything, it should be the capacitance, because dielectric helps the capacitance to be increased, all right, or helps the capacitance to go high, all right. Now, balance of the energy, never. Now, it actually regulates the current flow. So the answer is the dielectric of a capacitor is used to regulate the current flow. Determine the equivalent capacitance of the capacitors shown in the circuit. Now, these capacitors, this one, the 1 microfarad and this 1 microfarad, are in parallel because they are across each other. All right, so we're going to resolve them, all right, into a single capacitance. So now let's resolve them. That's going to be 1 plus 1. All right, so when you add them, that's going to be 1 plus 1. So it becomes this. So you're going to be left with this now. So adding this, combining this, you are left with 2 microfarad. That's 1 plus 1. Then this is 2 microfarad. So these two capacitors now are connected in series now. And I told you to find the total capacitance when two capacitors are connected in series. You use C1 C2 over C1 plus C2 to be very fast. So this is going to be C2 is equal to 2 times 2 over 2 plus 2. 2 times 2 of course gives us 4. 2 plus 2 gives us 4. So that's going to be CT is equal to 4 divided by 4 gives us 1 microfarad. So this is going to be our answer, 1 microfarad. Given 3 capacitors, each of capacitance C, the resultant capacitance of 2C over 3 can be obtained by A, combining all in parallel, B, all in series, C, 2 of them in series and in parallel with the third, D, 2 in parallel and the third in series with this combination. Now, which of these options is going to give us 2C over 3? Now, if you combine all in parallel, do not forget that each capacitance is C. So if you combine all in parallel, you're going to have C plus C plus C. That gives you 3C. And 3 See, it's not the same thing as 2c over 3. Now, the next, so this is out of it. So this is out of it. Now, let's try the next one. All in series. Now, if you try all in series, it is going to be 1 over ct is equal to 1 over c plus 1 over c plus 1 over c. Right? So that's going to be equivalent to 1 over ct is equal to 3 times 1 over c. Alright? 3 times 1 over c. No matter how you do this, you will never arrive at 2c over 3. So this is also out of it too. So we are left between option C and option D. Now, it says 2 of them in series and in parallel with the third. Okay, so it's saying that if you arrange them in 2 of them in series, all right, 2 first in series. Now, this is C, this is C. If you do this in series, it's going to be C times C over C plus C. So this is going to be C squared over 2C. Once C takes away 1C, you're going to be left with C over 2. All right. Now, C over 2. Now, this is for the 2 capacitors connected in series. So C over 2 now, then connected in parallel now. So it's going to be plus C. This is over 1. This is 2. This is 2 divided by 2, 1. 1 times C plus 2 divided by 1, 2. 2 times this. That's 2C. So that's going to give us 3C over 2. 3C over 2 is not the same thing as 2C over 2. So this is not also going to work. These are the 2 in series plus the 1 in parallel. All right. When you combine these two, all right, you have C over 2 plus the 1 in parallel gives you 3C over 2. So that is not also giving us our answer. It shows that this last one should be our answer. So C is also out. This last one should be our answer. But let's check it out. It says 2 in parallel. 2 in parallel, that means C plus C. We're going to have 2C. All right. So now you're going to have 2C and C. Now, in this is in part 2 in parallel and the third in series. So you have between this and this. So if you do 2C times C over 2C plus C. All right. 2C times C over 2C plus C. So this is going to be 2C squared over 2C plus C is going to give us 3C. 1C takes away 1C here, you're left with C. So you are going to be left with 2C over 3, which is what we need. So this is our correct answer. So when you combine 2 in parallel and the third in series, it gives you 2C over 3. So option D is our answer. That will be all for this video. Make sure you subscribe, share, like, and comment on this video. And make sure you hit the notification button after you subscribe so that when I upload more videos, you get notified. Thank you.